Hi, and welcome to Dr. V's AP Chemistry webcast. Today we're talking about intermolecular attractions, attractions between molecules that actually explain a lot about their physical properties. What I'd like to do today is talk about these key intermolecular forces: ion-dipole attractions, dipole-dipole attractions, hydrogen bonding, dipole-induced dipole attractions, and London forces. You need to know what kinds of particles can participate in all of these different intermolecular forces, and you also need to know how these intermolecular forces affect physical properties, especially boiling point. So let's start with ion-dipole attractions. As the name suggests, you need to have an ion interacting with a dipole, all right, or a polar molecule, another way of saying a dipole. So it is largely an electrostatic attraction, and the main point of electrostatic attractions is that opposite charges attract, like charges repel. So if I have a cation interacting with a polar molecule, the partially negative end of the molecule, which is shaded here in blue, is closer to the cation. But if I had an anion, the partially positive end of the polar molecule is closer to the negative ion, all right? And the opposite charges tend to be as far away from each other as they can. So we're trying to maximize attractions here. This is really important in terms of ionic compounds dissolving in water. As you know, most ionic compounds do dissolve in water, and when they dissolve in water, they dissociate into their ions. And this happens because the water molecules surround the ions, they solvate the ions. But what I want to point out here is that if you look at the blue cations, notice how the partially negative oxygen atoms of the water molecules are closer to the cations, and the partially positive hydrogen atoms of the water molecules are closer to the green anions, how the water molecules have oriented themselves around the ions. That's really important. These solute-solvent interactions can be explained primarily through these ion-dipole attractions, at least for salts going into water. We can use other intermolecular forces to talk about other solute-solvent interactions, but they do come back. So I just wanted to point that out because it's a really important thing to notice. So what happens is when salt is dissolving in water, the water molecules are colliding with the ions at the edge of the crystal, and they surround them and they go into solution. But again, noticing that the partially positive ends of the water molecules are attracted to the anions, and the partially negative oxygen atoms of the water molecules are closer to the cations. So just knowing that, you should be able to sketch that, okay? They are Coulombic attractions, right? And the two factors that affect the strength of Coulombic attractions are charge and distance. As the charges get larger, the strength of the attraction increases. So if we have a cation interacting with a polar molecule, all right, there's a certain amount of energy associated with that, the attractive force, all right? And if the cation had a larger charge, say 2+ instead of 1+, that would be a stronger attraction between the particles. Okay, so that's the first thing you look at with Coulombic attractions. You don't need to be able to do it in terms of writing out Coulomb's law, writing out the equation, doing the math here, but conceptually you need to know that as the charges increase, the strength of the attraction increases. The other thing that affects Coulombic attractions is the distance between the particles. If the particles are farther away, the attractive force gets smaller. So, and when they're very close together, it's a stronger attraction than when they're farther away. All right, all else being equal. Okay, so now let's go on and talk about dipole-dipole attractions. And as the name implies, you need to have polar molecules interacting here. All right, so they have to be molecules that are always polar. They always have a dipole moment. There's always a net separation of positive and negative charge. All right, and it is largely an electrostatic attraction. So the HCl molecule is very polar. The hydrogen is partially positive. The chlorines are partially negative, right? And the molecules orient themselves so that the partially positive hydrogens are attracted to the partially negative chlorines. And the partially negative chlorines are trying to be away from each other as much as possible because we're trying to maximize attractions and minimize repulsions, right? So you need to have two polar molecules and they're interacting with each other. The more polar the molecules are, the larger that dipole moment. Remember, we can quantify that if we choose, the stronger that attraction will be, right? It can be the same kind of molecule as in the HCl sample we were looking at on the previous slide, or they can be between two different kinds of molecules. So we can have solute-solvent interactions again, right? So I chose this picture because we've got acetone with chloroform. They're both polar molecules, right? The partially negative oxygen of the acetone is attracted to the partially positive hydrogen of the chloroform, right? And so we get an electrostatic attraction, right, between the partially negative end of one and the partially positive end of the other. And sometimes we choose to show these dipole-dipole attractions with a series of small dots, right? So the purple arrow is pointing to the depiction of that electrostatic attraction. So the two molecules are separate, and yet they're interacting with each other. They have this attraction to each other. All right. Now, hydrogen bonding is a particularly important situation, right? The first thing you need is a molecule where you have a hydrogen chemically bonded, covalently bonded to an oxygen, nitrogen, or fluorine atom. Now, this is important because oxygen, nitrogen, and fluorine are the very, very electronegative elements. And in this bond, they're attracting a lot of the electron density to themselves, which means the hydrogen's being left kind of bare in terms of electron density, right? And so that hydrogen atom gets attracted to a different molecule's oxygen, nitrogen, or fluorine atom because it's really seeking electron density on that other atom, and it makes an attraction between them. In fact, these are unusually strong attractions compared to your dipole-dipole attractions, all right? So I've got partially positive hydrogen atoms on one water molecule attracted to the partially negative oxygen on another water molecule, and we call this a hydrogen bond, right? H attached to O, N, or F, attracted to another molecule's O, N, or F. And this is stronger than your dipole-dipole attraction. And again, we're showing it here with a series of dashes, okay? It can be a very important part of solute-solvent interactions, but you have to meet this very specific definition. This is the classic definition of hydrogen bonding. So here I've got ammonia and water forming a hydrogen bond. The partially positive hydrogen in the water molecule is attracted to the partially negative nitrogen in the ammonia. And we've got that hydrogen bond between them. This is a little bit stronger than your dipole-dipole attractions, sometimes significantly stronger. And it can really be very important in terms of dissolving things. All right, so we've got that hydrogen bond there. You need to know this definition, and you need to be able to look at a formula and decide if this species could participate in hydrogen bonding or not. Make sure you draw that Lewis structure first, because just because there's a hydrogen atom in the formula doesn't mean it's attached to the oxygen, nitrogen, or fluorine. Very important in biology, base pairing in DNA, the anti-parallel strands of DNA are held together by hydrogen bonds between the base pairs. So that's what's illustrated here. It's also really important in protein secondary structure. So the alpha helix is held together by hydrogen bonds between a carbonyl group and an amine group on amino acid 4 amino acids away. And we have a whole series of these, and they hold the helix together. Beta sheets are held by strands of amino acids forming hydrogen bonds sort of between the strands, and that's holding the beta structure together. So they're really important. So even though these are all happening within the same macromolecule, we do, of course, still consider them hydrogen bonding because it's far away. So the next type of attraction I'd like to talk about are dipole-induced dipole attractions. So what you need here is a polar molecule interacting with something that is not polar, all right? And the reason this happens is that a polar molecule can temporarily distort the electron cloud of a nonpolar atom or molecule. So what I've got here in the picture, I've got an image of a oxygen molecule, and it's just hanging out. Its electron clouds are, it's very symmetric. It's very uniform. There's no partial positive or partial negative region for an oxygen molecule, certainly when you look at a time average. If a water molecule approaches, let's say it's coming in so that its partially negative oxygen atom is coming close to the atoms in the oxygen molecule. Well, the electrons in the oxygen molecule are repelled by the partially negative oxygen in the water. And they kind of move to the other side of the molecule temporarily, right? That's because we know light charges repel. It makes the right-hand side of this molecule partially negative, and here the color coding is that it's pink, leaving the left-hand oxygen in the oxygen molecule without much in the way of electron density. It's partially positive. Well, now we have a partially positive region attracted to the water molecule's partially negative region, we can have an electrostatic attraction here. All right. When the water molecule leaves, the oxygen atom goes back to being nonpolar. Like an oxygen molecule is a nonpolar species. Its time average is that its electron cloud is symmetric and evenly distributed, but we can distort it. And this is a dipole-induced dipole attraction. All right, so you do need to have a polar molecule with a nonpolar species. All right, so here's just the same species oriented slightly differently relative to each other, but it is a very temporary thing. When that water molecule goes away, of course, the attraction stops. This is really important in terms of dissolving nonpolar gases in water. All right, this is what happens when oxygen gas is dissolved in water. The fish are all very happy about that. A similar situation for carbon dioxide being dissolved in water. So if you're really into your carbonated beverages, right, it's all about dipole-dipole attractions. The water is inducing a dipole in the nonpolar CO2 molecules, and that's enough to keep some CO2 molecules dissolved in the water. Now I'd like to go on and talk about something called an instantaneous dipole. Okay, we've got a picture here of a nonpolar atom, right? And the electron cloud is pretty symmetrical, and their electrons are hanging around, just doing their thing, moving around randomly as electrons do. But at any moment in time, those electrons could both just accidentally, randomly end up on the same side of the atom. All right, so it's a temporary distortion here, which means my electron cloud is partially negative on the left and partially positive on the right, just due to random motions. All right, so we have this short-term uneven electron distribution. As long as the electrons are sort of hanging out both on the same side temporarily, time average though, it's still a neutral nonpolar species. So if an atom experiences an instantaneous dipole, because both electrons end up on the same side, and it ends up having, temporarily a partially negative region and a partially positive region, it can then induce a dipole in its neighbor. And now one side of one is partially positive and one side of the other is now partially negative, and there's a very temporary, very weak electrostatic attraction between them. Now, time average, both of these species are nonpolar, but there's enough here to hold the particles together weakly. Okay. One thing I do want to mention is that all matter, ions, polyatomic ions, all kinds of polar molecules and nonpolar species can participate in London forces. However, they only really matter if that's the only thing that those particular species can do. The other attractions are stronger. And so if we get these temporary distortions and then they induce a temporary distortion in their neighbor, and then there's a whole bunch of them doing this, that can actually help hold the species together. All right. But the only time they really matter is when London forces are the only thing that you can do. So if you have a nonpolar molecule like oxygen interacting with a sample of other oxygen molecules, they only can do London forces. The halogen molecules can only do London forces. All matter can do them, but if you can do hydrogen bonds, if you can do dipole-dipole attractions, those are much, much stronger, and they're going to usually have a much more significant effect. All right. Now, when we talk about the strength of London forces, the term you really need to focus on is polarizability. How easy is it to distort the electron cloud? How squishable is it? All right. The more electrons are in that electron cloud, the more polarizable that electron cloud will be. And when that electron cloud is squishier, more polarizable, that's the word you really need to put into your free response answers, the stronger the London forces will be, the stronger those attractions will be. All right, if the electron cloud can be distorted more. So if we look at the halogens, if we go from fluorine to chlorine to bromine to iodine, all right, as we go down the column and we have more electrons in the electron cloud, we see that the boiling points go up considerably. A higher boiling point means it takes more energy to separate them into the gas phase, which would mean a stronger attraction. All right, so the College Board really wants you to focus on more electrons being more polarizable, giving you stronger London forces. They do not want you to talk about the mass of the particles. They really want you to talk about the polarizability of the electron cloud. Please remember that. That'll help you score that point. right? The shape of the molecule also has an effect. This is a more subtle point and not something that the College Board emphasizes, but as you go on and take more chemistry, it will come up more. But more compact molecules are less polarizable than long, thin chains, right? And what we have to remember is that when the London forces are stronger, the boiling points will go up, all right? It'll be harder to get them into the gas phase because the attractions are stronger, right? So if we look at N-pentane, all right, which is C5H12, right? N meaning all the carbon atoms are in a chain, all right? It's got a boiling point of 36 degrees. If we look at isopentane, which is also C5H12, but a slightly different structure, right? Its boiling point is lower. And if we look at neopentane, which is also C5H12, but it's an almost spherical molecule, its boiling point is down to 9. So these guys all have the same molar mass. They all have the same chemical formula, but the long, thin chain of N-pentane has a more distortable, more polarizable electron cloud than neopentane, and that's why we see this pattern in the boiling points. So that's an important thing to remember as well. All right, so the shape of the molecule does affect it. I think, though, the College Board is much more likely to talk about the number of electrons, a larger electron cloud being more polarizable than to talk about the shape. IMFs do have a significant effect on physical properties as well. So if we look at propane versus ethanal, an aldehyde, or ethanol, all right, we see a huge change in boiling points. So the alkane, which is all nonpolar, it can only do London forces. And notice its boiling point is really low. The attractions between the particles are very small. When we have that carbonyl group in there for the aldehyde, right, it's now a polar molecule. So it can do dipole-dipole attractions as well as the London forces. The dipole-dipole attractions are significantly stronger, and notice the significant increase in boiling point. You have to get everything to you need to put more energy in to get these molecules into the gas phase if you have a pure sample of ethanol. And finally, we have ethanol, the alcohol, and it can do London forces. It's a polar molecule. It can do dipole-dipole attractions, but now, right, if you look at the hydrogen, it's bonded to an oxygen. It can be attracted to the oxygen of another ethanol molecule. It can do hydrogen bonding. And notice that the boiling point has gone up significantly, right? So in general, we see that hydrogen bonding is stronger than dipole-dipole attraction. They're definitely stronger than London forces, right? And that's a general pattern that we see. However, all right, there are sometimes problems where they give you structures and boiling points and ask you to infer which ones have the stronger intermolecular forces. If they have a higher boiling point, right, then they have the stronger intermolecular forces, even if it doesn't, even if that doesn't mean the one that can do dipole-dipole attraction might not have the stronger boiling point or the higher boiling point. There are times where there's a discrepancy. So you have to remember, higher boiling points mean stronger intermolecular forces, regardless of the formulas of the compounds. And there are times where the College Board is specifically looking for that explanation of that discrepancy. So in terms of wrapping up, make sure you can look at the chemical structure and decide, is it polar, non-polar, right? What kinds of intermolecular forces could that particular substance participate in? If it's in a pure sample, what could it do if it were with water or with another solvent? And species with higher boiling points, regardless of the nature of the IMFs, must have stronger attractions. If you haven't subscribed to my channel, please go ahead and do that now. I'd really appreciate it. Thank you. Have a great day.